we spend a long time on learning linear map. One sad thing of linear map is that it is a unary map, so it has only one input and one output. But we have learned that there are also bilinear, trilinear, so there are n-ary functions. So we want to extend the concept of linearity in such a case. For this case, we need some domain. Let us say v1 plus 1 and heart 1 and vn plus n heart n. And then we can have this Cartesian product vector space. And then we also have some w plus heart. It is a target, so w. We can define this map. And what we want is that this to be a map called multilinear. So I want to define multilinear map. Multilinear map. Then we have a map, so we have a domain and target. What is remaining is that we want to find some property the operation should satisfy, because we want how addition and how multiplication changes. Multilinear map is defined like this. First, let us say set some number a, k, and also let us write also for I 1 to n. We have ui, vi is in vi. So we have this and this. Then phi for the first slot, a heart 1 u1 plus v1. So this is first slot, and this guy comes from this, and Cartesian product is that we make some ordered pair. So others are just v2 and vn. And what we call multilinear is that this is the addition and addition and as multiplication in the domain. So what we want is that this becomes a heart phi u1 v1 v2 vn plus phi v1 v2 vn. So now it becomes as multiplication and addition in the target space. And what we want is that this is true for also v1 comma a heart 2 u2 plus v2 comma v3 comma vn. This is also a heart phi v1 u2 v3 vn plus phi v1 v2 v3 vn, and this hold for every slot. For the final slot also v1 vn-1 comma a heart n un plus vn. Then this becomes also a heart phi v1 v2 un plus phi v1 v2 vn. So addition and s multiplication in each slot. Sorry, I forget 2 here, 1 here, so n here. So addition and s multiplication in each slot, and target becomes addition and S multiplication in the domain of each slot becomes addition and S multiplication in the target space. So now we know how the operation changes by the map. If the map satisfies this relation, this is called multilinear. Then can you say multilinear is also linear? I say it's not. Multilinear, linear is not linear. Let us go some simple example. V1, let us say V1 times V2. Phi is map V1 times V2 to W. Recall that this is Cartesian product vector space. Then we have V1 times V2, comma, plus, let us write just 1, 2, and heart 1, 2. And if you remember heart 1, what is heart 1, 2? For A in K, A heart 1, 2, and also some vectors V1 in V1, V2 in V2, we have, okay, I write this guy, I move this guy to the left, this guy to the right, this guy to the up. Okay, A heart 1, 2, and V1 comma V2, because this guy is in V1 times V2, and this is defined in each slot. A heart 1 V1 comma A heart 2 V2. So now we have this guy, and the role of this guy becomes everything in here. The question is that, what if, let us say phi is a bilinear map, so multilinear. Especially when it is just 2, it is called bilinear. So when phi is bilinear map, let us see what happens. Phi V1 comma V2, phi A heart 1, 2 V1 comma V2, and it becomes phi A heart 1 V1 comma A heart 2 V2, and it is let us say from the linearity phi A heart phi V1 comma A heart 2 V2, and it is A heart phi V1 comma V2. And from the associative, we have, this is just A square heart phi V1 comma V2. But for linear function, this should be phi, because S multiplication just needs to be come out, so phi V1 comma V2. Definitely these two guys are different because it is A square, one is A. So bilinear is not linear map. So the reason is that in here, multilinear, each slot as multiplication and addition becomes target space operation, but in here, the full operation in the domain becomes full operation in the target space. That makes the difference. So I think it's good to know that they are different. And okay, so this is what we call multilinear form map. And if there are many multilinear map you meet in the physics, in fact, what we call tensor is what I in my mind, tensor is nothing, just a just a multilinear map. So tensor is a multilinear map. Also, some inner product or wedge product, they are all some multilinear map. So there are many things appear in many calculations or concepts appear in physics are in fact multilinear map. And usually in physics, some inner product or something, you don't have get some different space element to apply. For example, kinetic energy is just v square, and when you calculate it, you have just v times v. The v is the same element. So what we are interested is the domain is just the Cartesian product of itself. So some form of like Vn. So the most familiar important guy is domain is this guy. And also we have learned that target, of course target can be another same thing, but like inner product, this is the, I think, one of the most important cases. And this is form, because if it is 1, it is called 1 form. It is now n. We might say it is n form. So in fact, this is called multilinear form. And in this special case is n form, or as I told you, it is tensor. So this special case is phi is covariant. Covariant means that it is form and n tensor, or just n form. This is and the most interesting is that when n is 2, this case phi v square to k, because this appears so much times, we call this just the bilinear form. So bilinear form is just a bilinear map from the same domain, Cartesian product of the same vector space, to the some field. And it's time to see some example. So again, integration. And what you familiar? Let us say I is now v squared to k, and also it is a definite integration. But now f and g, we have two elements. It is just 0 to 1. Oh, I forget. V is the same. V is a set of continuous linear functions, fx, gx, dx. This is some example of a bilinear form. So you get two vectors and get number, and you can have each addition and multiplication in each slot becomes the here. And also there is some special with the bilinear form. You can define quadratic form. Sorry, it is some definition. I think this is just some nice example of showing that bilinear form is not linear because it is like this, and then it is just bilinear form. Then let's say Q, because it is quadratic, V to K by V in V, QV is defined just phi VV. Maybe I'd rather write here phi VV. Then because this is number, so this is good, nice well-defined map. And this is called quadratic form, and it is not linear because you can see from for I, let us say using I, so QF is integral f square dx. If you put QAF, it becomes integral AF square dx. It is A square integral f dx, and this is A square QF. This is why it is called quadratic, because you put just A, it becomes A square. And okay, this is called quadratic form. And also, because we put only one number and get one vector and get one number, it is the one form we learned before. Oh no, it is not one form because it is not linear. Sorry, it is just some other thing. It is called the form, but not one form. And now I define some slot notation. Then can we find, because it looks like some, it was form, but unfortunately it was not linear one form. Question is, can we find some one form from this multilinear form, bilinear form? The answer is yes. And how to do it? It is defining some slot using slot notation. So let us write something like this. First, let us assume we know v square to k, and for given this v square to k bilinear form, define phi vl is v to k, so it is an element of one form, so it is one form such that for all w in v, phi vl w is phi v comma w. Similarly, then you can think what is L? L is just left. Then you can define right. It is also one form such that for all w in v, phi v r w is phi w comma v. So now you know what is left and right means. It is just the position of v. And these are linear map in this case, because now you have just one addition and s multiplication, which is in the second slot or first slot in each case. So one addition and one S multiplication becomes one addition and one S multiplication in the target space. So now it is really a one form. If you don't believe me, you can check. And there is also a name called the radical. So there are two radicals. Left radical is radical phi. For given bilinear map, we have a left radical. It is just V in V, intersection of all corners of phi VR. So it is set of vectors which is 4V phi VW is 0. Radical of right radical is same, but with the phi r instead of r. So it is just a set of vectors, and for v in v, phi wv is 0. So this w, if there is some radical, the element of radicals are the vectors which gives always 0 for this bilinear form. So then there are some boring part of bilinear form, and usually we don't want it. So we call it non-degenerate, the interesting case. Non-degenerate means that, so we call phi v square 2k is bilinear. Let us say this is bilinear. Linear. This bilinear form is non-degenerate. Is non-degenerate if and only if radical of left radical and right radical is 0. Sorry, trivial. So it has only 0 vector in V. Then it is called non-degenerate, and other cases are degenerate. So we are always interested in non-degenerate cases. And the other definition, what we are interested is called symmetric bilinear form. So symmetric bilinear form is that now also for bilinear form, then for V1 and V2, let us say that they are element of V. If phi V1 V2 is phi V2 V1, then bilinear form phi is symmetric, chord. So this is what we call symmetric for the bilinear case. So phi is, we say just phi is symmetric bilinear form. And of course this trivial 0 map, so we can also say 0 map K by, also we always can everything to 0. This is symmetric because anyway V1 V2 0, V2 V1 is 0, so they are 0. And the other more non-trivial example is that 4 vector product. It is just in the special relativity when you run, let us say some v has coordinate v0, v1, v2, v3, and w has also coordinate w0, w1, w2, w3. Then what we have learned is that in special relativity, there is some invariant length which defined by v0, w0 minus v0, w0 plus v1, w1 plus v2, w2 plus v3, w3. This is also symmetric. You can easily check by just changing the order of multiplication in each term. This is also symmetric bilinear form. This is called Minkowski inner product or Lorentzian inner product. But in fact, this bona fide inner product is not inner product. So then let us see what is inner product then. The inner product is for a given vector space v w hat plus hat, and inner product is we usually use this dot notation for the unique Euclidean space or real vector space. This is v square to real number. It is non-degenerate, positive, definite, bilinear map, symmetry, bilinear map. Now we run new word, positive definite. Positive means that, okay, positive means that for all v in v, v dot v is always bigger than 0. Recall that for the bilinear map, we sometimes use it in the between. So this is just that v. Instead of we write this we write this. And definite means that for v, if this is 0, this is means that v is 0. This is what we call definite. So positive definite is just to be combined this together. And so we finally have inner product, or in also its nickname dot product, because we usually use dot for it representing it, or some scalar product because it is result is scalar. This is what you run, what you first run in the when you run vectors. You have some there is dot product of two vectors product, and they give scalar, and it is some a b, then a it gives a b cosine theta. But in fact, it is some extra structure. You don't need inner product to define vector space. It is just simple and intuitive thingy, but very higher level concept, because you need to know the bilinear. So bilinear map, which is non-degenerate, and you need to also know positive, you need to know definite, you need to know what is symmetric, and you need to know everything until now we talked. And this is called inner product. Now I will extend it to more general case, but I think it's too long, so I stop here.